Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Arusi, and today today is the first of our Year 13 sessions for the new academic year. And in this session, we're going to be reviewing organic reaction mechanisms. We're going to start by looking at the principles underpinning the use of curly arrows, and then we will apply these principles to the electrophilic addition mechanism, the nucleophilic substitution mechanism, and as always, we will be looking at some practice exam questions on these two mechanisms. We will also look at the one mechanism where the curly arrow isn't required of you. We will be looking at the radical substitution mechanism. I'm sure you knew that. And as usual, I will ask that you, if you have any questions at all, to use the chat box and to write your questions in there. I will pause at regular intervals to answer your questions. We're all set to go. If you give me a few seconds, I will connect my tablet and share my screen with you, and then we will be on our way. So a few seconds while I do that. Okay, so you should be looking at my title page, which is saying AS Organic Reaction Mechanisms. And this is a Year 13 live session reviewing all of the organic reaction mechanisms you saw in your first year. So where do we start then? A good place to start would be to look at how bonds break in molecules. And there are two ways for the pair of electrons in a bond to be sort of prized apart from the two atoms bonding together. The first is homolytic fission, and in homolytic fission you get one electron from the bonded pair going to one atom and the other electron going to the other atom. So the electrons are divided evenly between the two so that you end up forming two radical species. So it says each bonding atom receives one electron from the bonded pair and two radical species are formed. So let's have a look at what these radical species look like. So in the case of the chlorine molecule, you've got a covalent bond between two chlorine atoms. That covalent bond, of course, contains a bonded pair of electrons. So if we use half-headed arrows to show the movement of a single electron, you're not required to use these half-headed arrows on the OCR course, but it gives you, I guess, something analogous to the double-headed arrow, curly arrows that you've been using in your reaction mechanisms. So as a result of that bond breaking homolytically, you're going to form two chlorine radical species, and the radical species are shown with the single unpaired electron that they have, which of course is what defines them as radicals. Okay, so a radical is a species with an unpaired electron. Okay, so bonds can break homolytically, and of course the other way that bonds can break is through heterolytic fission. Now in heterolytic fission, both electrons in forming the bonded pair will go to one atom, and the other atom, it becomes electron deficient. And as a result of this, you get ions being formed. Okay, so if we look at the definition of heterolytic fission, it says one bonding atom receives both electrons from the bonded pair, and you form ions of opposite charge. Okay, so if we look at this example involving hydrogen chloride, if we have heterolytic fission, in this case, your chlorine atom being more electronegative will have both electrons going to it, and this will leave us, so this is the dissociation of our hydrogen chloride molecule, and this is exactly what will happen if you dissolve it in water, so that you're going to have an H plus ion, and you're going to form a chloride ion, Cl minus. Okay, so this is heterolytic fission. So this sort of introduces the idea, or this mechanism, not a mechanism, but this bond breaking process we've just seen introduces the idea of the curly arrow. And this curly arrow is showing the movement of the pair of electrons in our bonded pair towards the chlorine atom to form the chloride ion. Okay, so bonds break and bonds also form in our in reactions, and in organic reactions we're going to be using the curly arrow to show how these bonds form and how these bonds break. So let's look at a few principles governing how you should be using the curly arrow. Okay, so first of all, the curly arrow has to be curly. That's its name, right? This is because you don't want to confuse it with a reaction arrow. Okay, so if you're showing your curly arrow, make sure that it's unambiguously curly rather than having a straight arrow. So as you can see here, we've got different types of curly arrows, all mean the same thing. They're showing the movement of a pair of electrons, whereas this straight arrow is just a reaction arrow showing going from reactants to products. So don't use a straight arrow when you're showing a mechanism, and you need to show curly arrows instead. Okay, so the curly arrow must be curly. It shows the movement of a pair of electrons, and it shows what bonds are being formed and what bonds are being broken. And finally, I think curly arrows must start from a source of electrons. If we're tracing the movement of a pair of electrons, then logically our curly arrow has to start from a source of electrons. Okay, so that is a key sort of factor that that is a key point, I should say, that some students miss out, perhaps through carelessness or perhaps sort of not quite understanding what the curly arrow signifies. Okay, so if you're checking through your mechanism, you should be doing this out of habit. Having drawn a mechanism, you need to check it. Make sure that your curly arrows are starting from the right place. So sources of electrons will be a lone pair of electrons, or it could be a bond. Okay, for instance, the pi bond in your double bond. Okay, so let's look at this example here where you've got the hydroxide ion, which is shown down there. You've got the hydroxide ion reacting with this halogenoalkane, so this is bromoethane. Okay, and we'll look at this mechanism again shortly. And what you want to do is show the movement of our pair of electrons in the lone pair towards that carbon with a delta plus charge, or partial charge on it. Okay, so that is showing the movement of a pair of electrons. The result of this movement of a pair of electrons ultimately is that the carbon-bromine bond is broken. Okay, so this is what happens as a result of your hydroxide attacking the carbon with a delta plus on it. The CBr bond gets broken, and we now have an alcohol as our product. Okay, so if we say color scheme, got OH here, and you will have Br minus as your other as your inorganic product. Okay, so curly arrows have to be curly. They're going to show the movement of a pair of electrons. They'll show what bonds are being formed and what bonds are being broken. So we formed a new bond between the oxygen and the carbon, and this is that bond there. We've broken the carbon-bromine bond, that one there. Of course, we now have a bromide ion as a result. Okay, so 4 very simple principles which you must rigorously apply for all the mechanisms you've seen at AS and all the mechanisms you're about to see at in your A level, so in your second. Okay, so let's have a look at some other mechanisms then. So one of the first mechanisms, curly arrow mechanism you come across is the electrophilic addition mechanism. And this, of course, is the mechanism that sees your alkene double bond reacting with an electrophile. Okay, so perhaps at this stage it is worth defining what an electrophile is. Okay, so an electrophile is, and you should know this by now, if you don't, an electrophile is an electron pair acceptor. Okay, so in this electrophilic addition, we're going to add an electrophile across the carbon-carbon double bond. And so in this instance, our pi electrons in our carbon-carbon double bond, the pi bond, are going to be our nucleophile. Okay, and nucleophiles, of course, are electron pair donors. Okay, so okay, so we've defined electrophiles and nucleophiles. Well, let's have a look at this reaction then. You've got our nucleophile, in this case an alkene, and it is going to be reacting with hydrogen bromide to form bromoethane. Okay, so how do we go from this alkene to this bromoethane, which is, of course, a halogenoalkane or haloalkane? Now, here is our electrophile. It is hydrogen bromide, and hydrogen bromide is, of course, polar. It is polar because your bromine atom is more electronegative than the hydrogen atom, and so the electron density is towards the bromine atom. And so you've got a delta minus on the bromine and a delta plus on the hydrogen. So your electron pair, remember your curly arrow has to start from a source of electrons, and this source of electrons can be a bond or can be a lone pair of electrons. In this instance, the alkene is going to be supplying the pair of electrons, and specifically the pair of electrons that make the pi bond in your double bond. So your curly arrow has to start from the middle of the double bond, and you can show that curly arrow attacking the hydrogen of your hydrogen bromide. The consequence of that attack on the hydrogen of your hydrogen bromide is that the HBr bond is going to break. Okay, so the HBr bond breaks, and again, you're showing the curly arrow starting from the middle of the HBr bond and ending up on the bromine atom. Okay, so what is the result of these two curly arrows being drawn? The result, of course, is that you've broken the pi bond of your double bond, so you no longer have a double bond. You have formed a bond between one of the carbons and the hydrogen, and here we have it here, the CH bond. And because this carbon here no longer has a pair of electrons between it and the other carbon atom, we've broken the pi bond heterolytically, this carbon atom is now electron deficient and has a plus charge on it. So we formed what is known as a carbocation. So it's a carbon atom with a plus charge on it. It's a carbocation. And we've also formed a bromide ion. Okay? Now, there's a very important principle at play here, which we need to discuss, and this is that of the conservation of charge. Now, as you can see here, before our arrow here, so in this part of our equation, there is no overall charge. Okay, so the alkene is uncharged, it's neutral, and the HBr, although it is polar, it's neutral overall. It isn't ionic. Okay, and that means that when you make a carbocation as an intermediate here, you need to have that plus charge being cancelled out by another species, and of course that is the bromide with its minus charge. Okay, so charge is conserved. The plus here and the minus here cancel each other out so that there's no overall charge here. That is another thing you must make sure of sort of checking when you do a reaction mechanism. That charge is always conserved. If there is a plus charge to the left of the arrow, then there must be a plus charge to the right of the arrow. If there's no overall charge to the left of the arrow, then there's no overall charge to the right of the arrow. Okay, something to bear in mind and rigorously apply. Okay, so we now have our intermediate carbocation and we have our bromide ion. So the next part of our mechanism shows attack by our bromide ion at the carbocation carbon. So you're forming a bond between that carbon with a plus charge and the bromide ion. Okay, so as a result of that curly arrow that I've just drawn here, you're going to end up forming a CBr bond. Okay, and that concludes our electrophilic addition mechanism. Okay, so it's fairly straightforward. Remember that your first curly arrow starts from the pi electrons, which is a source of electrons, and they attack the hydrogen of your HBr, causing the HBr bond to break. You form a carbocation and you form your halide, in this case bromide, and then the two combine to form your CBr bond. Okay, so I think at this stage it might be a good idea to see if there are any questions in the chat function or chat box, I should say. Have a quick look. Okay, so there are no questions so far, which is good. We have a little. Okay, that's fine. Okay, so we will carry on with our work then. So let's have a look at another variant of the electrophilic addition mechanism. Okay, so this time round we don't have ethene. What we've got here is, of course, if I can do that for a second, use the wrong pen. There we go. So what we've got here is propene rather than ethene. And this presents a problem because propene is asymmetric. Okay, so if we go back one screen to the first alkene ethene, you can see that it's completely symmetrical. The double bond is between two carbons, and you've got each carbon with two hydrogens bonded to it. Here, you've got the double bond between the two carbons. This carbon has got two hydrogens. This carbon here has got a hydrogen and a methyl group bonded to it. Okay, so there is a lack of symmetry. There is an asymmetry there. And that means that there are two possible carbocations you can form. Okay, so you can form this carbocation here, and you can also form this carbocation here. Now, the question is, which of these two carbocations is going to be the more favored and would lead to the major product? Of course, that major product is formed from this carbocation here, which is the secondary carbocation. Because why is it a secondary carbocation? It's because this carbon here has got two methyl groups, two alkyl groups bonded to it. This here is a primary carbocation because it's only got one alkyl group bonded to it. Okay, now there is a significant difference in stability between this secondary carbocation and this primary carbocation. Okay, so why is there this difference in stability? Well, before we answer that question, let's draw the first part of our mechanism first. So as we said on the previous page, what you need to do is show your curly arrow starting from a source of electrons. Because this is an electrophilic addition mechanism, it's going to start from the pi bond of your double bond. Okay, so here's our curly arrow finishing up at the hydrogen. Why? Because the hydrogen has a delta plus on it, while the bromine has a delta minus on it. And as a result of our attack on the hydrogen, your HBr bond is going to break, and you're going to form a bromide ion as a result. So there's your bromide ion there. And of course, here is your carbocation as a result of your pi bond being broken. Now, if we look at the second alternative, again, you've got your curly arrow starting from the pi bond going to the hydrogen, which is of course delta plus, and Br being delta minus. And just as we saw before, your HBr bond is going to break, and so you have a bromide ion being formed, and of course you've got a carbocation. This time round, you've got a primary carbocation. The plus charge is on the end carbon, and there's only one alkyl group attached to that end carbon. Okay, so why is a secondary carbocation a lot more stable than the primary carbocation? Well, it comes from the fact that alkyl groups like to push electrons away from themselves. So here I've shown our carbon cation as a skeletal structure. And here's one of our methyl groups, and here is the other methyl group. And as you can see there, you've got both methyl groups pushing electrons towards that carbon with a plus charge on it. Okay, that is something that alkyls do. They push electrons away from themselves towards other species. Now, the more alkyl groups you've got, the more electrons are going to be pushed towards that plus charge, and so the smaller or lesser that plus charge becomes. The less of a positive charge it is, the more stable it is. Okay, so that carbon cation is more stable thermodynamically, it's going to be forward. Now, this pushing of electrons away from the alkyls towards that carbon with a plus charge is known as the positive inductive effect, which I've shortened to PIE here. I'm going to spell that out for you. Okay, so this is the positive inductive effect. Okay, so there is a greater positive inductive effect for your secondary carbon cation compared to your primary carbon cation. So if we look at our primary carbon cation here, you've got your alkyl group. Yes, it is an ethyl group, but there's only an inductive effect coming from this one alkyl group. Okay, so this isn't going to be, that plus charge isn't going to be as stabilized as your second, the plus charge on your secondary carbon cation. Okay, so the primary carbon cation has a smaller positive inductive effect and will be, as a result, less stable. Okay, so your secondary carbon cation is going to lead to the major product, while your primary carbon cation is going to lead to the minor product. So when we talk about the major and minor product, we're talking about the relative proportions of the two products to each other. So a much larger proportion of the yield is going to be your 2-bromopropane versus the minor product, which would be 1-bromopropane. So here's 1-bromopropane shown here. Okay, so that is the electrophilic addition mechanism for an alkene that is asymmetric. Okay, now again, I will pause to check for questions. If there are any questions, let's have a quick look on YouTube. Okay, so no questions for the minute. So what we will do then is move on to the next mechanism. Right, so let's have a look at the nucleophilic substitution mechanism, the second of our curly arrow mechanism that you will have encountered in your first year of A-level study. Okay, so we saw the nucleophilic substitution mechanism a few slides ago, but I didn't describe it as such. So let's look at why it is a nucleophilic substitution mechanism. So on your screens, you've got a reaction between this bromoalkane and aqueous sodium hydroxide. And the resulting product, the organic product anyway, is this alcohol here, ethanol. And the inorganic product is sodium bromide. Now, how does this product form? Clearly, there must be a bond formed between an OH minus ion from your sodium hydroxide, and as we can see, there's no Br in our product, so this bond here must be broken. Okay, so why should this OH minus ion form a bond to the carbon that has a bond to bromine atom, is the question. Well, it goes back to the fact that your CBr bond is polar. Okay, so there's a delta plus on the carbon and a delta minus on the bromine atom. Why? Because the bromine atom is more electronegative than the carbon atom. Okay, so we do have a polar CBr bond. As a result of that polar CBr bond, our carbon atom in the delta plus is very susceptible to attack by nucleophiles. We described on the previous page that a nucleophile is an electron pair donor. Okay, so there's a pair of electrons on your hydroxide ion that can be donated to form a bond between the oxygen and the carbon atom of the CBr bond. Okay, so the first curly arrow we're going to draw is going to be from the lone pair of our OH minus ion, on the oxygen of our OH minus ion, to the carbon of our CBr bond. Okay, having drawn a curly arrow, the resulting the consequence of that curly arrow, or that bond between the oxygen of the OH minus ion and the carbon, is that the other bond, the CBr bond, has to be broken. So, curly arrow from the middle of the CBr bond to the bromine atom, and this, of course, leads to our product, the OH group being bonded to your carbon to give you ethanol, and the bromide ion being formed as our leaving group. Okay, so in this reaction mechanism, what we've done here is substituted the bromine atom here with, or replaced it with, an OH group. Okay, so it is a substitution mechanism, and it is caused by this nucleophile, so this nucleophilic attack to that carbon there. So we have a nucleophilic substitution mechanism. Okay, so quite a straightforward one for you to follow. And you probably will encounter lots of different kinds of nucleophiles. So the OH minus ion is one example. You might see in some examples a cyanide ion acting as a nucleophile. Sometimes you might see a thiol, which is a bit like an OH minus ion, but has got sulfur instead as your donor of lone pairs. You can, of course, have ammonia, where the nitrogen has a lone pair to donate. And so nucleophilic attack comes from your species with a pair of electrons, or a lone pair that it can donate to our electrophile. The electrophile in this case is our halogenoalkane, and the electrophilic carbon is that carbon of your CBr bond. Okay, so that's our nucleophilic substitution mechanism. And of course, there is one mechanism in your AS year that does not involve curly arrows, and this mechanism is, of course, the there we go. So this mechanism is a radical substitution mechanism. Before we come to the radical substitution mechanism, I just want to go through a checklist with you. So having drawn a reaction mechanism, what are the questions you need to answer to be satisfied that you've got the correct mechanism shown? Okay, so are your curly arrows, we do that for a second, there we go. Are your curly arrows curly? Okay, so here are my curly arrows in this mechanism, and as you can see, they're all curly. There's no way you can mistake them for reaction arrows. These are my reaction arrows, they're all straight. Okay, so far so good. So far so good. Do your curly arrows start from a source of electrons? So here's my first curly arrow starting from the pi electrons in our double bond. Here's my second curly arrow starting from the middle of the HBr bond, so showing the HBr bond breaking. Here's my third curly arrow starting from the lone pair of my bromide ion and attacking the carbon of our carbon cation, and to the carbon with a plus charge, and as a result forming this CBr bond. Okay, so all of my curly arrows start from a source of electrons. None of my curly arrows are starting from a positive atom, so a positive ion, or from a neutral atom. Okay, so the next thing to answer, or the next question to answer, is where do your curly arrows end up? Okay, so you need to be very careful that your curly arrow isn't drawn to something that has a negative charge on it. Okay, so this curly arrow is attacking our delta plus, and you're breaking that bond, and the bromide, being more electronegative, accepts both electrons from that bonded pair, so it becomes that Br minus species. Okay, and that curly arrow again is attacking something that is positively charged. Now, making sure that your charges are balanced, in other words, conservation of charge. There is no overall charge on this side of the arrow, and over here there is no overall charge either. You've got plus cancelled out by a minus. Okay, so charge has been conserved in drawing this mechanism. And finally, check that your curly arrows are not meeting head to head, because that would imply that you've got two pairs of electrons coming together. Of course, we know that they're going to be repelling each other, and that will not happen. Okay, so all of my curly arrows are following sort of each other, so head to tail, and so that is the only instance where you've got two curly arrows, so back to back. So you've got that head attacking and that tail sort of leaving, like so. Okay, so make sure that you don't get clashing curly arrows in your mechanism, because that is a sure sign that your mechanism is incorrect. Okay, so having run through that checklist, I'm happy that I've got full marks for this mechanism, and so we can move on to our next mechanism, which is a radical substitution mechanism. And that, of course, involves the other kind of bond fission that we mentioned right at the start, homolytic fission. Okay, so here we've got the chlorination of our methane, and in the process we're going to be forming chloromethane in the first instance, and hydrogen chloride gas. So how does this happen? Well, the first step in this mechanism is referred to as the initiation step, and this requires the formation of radical species. So your Cl2, you write it out as ClCl, is going to be broken down, or the ClCl bond is going to be broken homolytically, and this happens in the presence of UV. Okay, so an important condition for radical substitution to form a halogenoalkane is that UV light has to be present when your chlorine or your halogen is reacting with an alkane. Okay, so we need UV light, and that UV light is providing the energy needed to form two chlorine radicals, each of course with an unpaired electron, which is what makes them radical species. So both of these radicals are formed because of UV action on this bond here. Okay, so there's your radical species form. The next step is the propagation step, and this propagation step involves our CH4 molecule. I'll draw it out in full as displayed formula. Our CH4 reacting with one of our radical species. Okay, and the result of this first propagation reaction is that a CH3 radical is formed, and our first molecule of HCl is also formed. And then in a second propagation step, the radical you formed in the first step is going to be used to react with a chlorine molecule. So CH3 radical reacting with another molecule of chlorine, and in the second propagation step, you're going to have the CH3Cl molecule formed, and you're going to regenerate chlorine radical. Okay, so there's your propagation step, requiring the reaction of the chlorine radical with our alkane. So this is what's going on here, to form a methyl radical and HCl. And then in the second step, our methyl radical reacting with another molecule of chlorine, and in the process forming our chloromethane and regenerating our chlorine radical. Now, there are a number of termination steps that you can write. We'll write all three of them for this particular reaction. You can have so a termination step that involves two radicals coming together. So two radical species coming together and forming a bond between them. So you can have the obvious termination step where your chlorine radicals reform chlorine molecules. So Cl2 is formed from Cl dot plus Cl dot. You could also have a methyl radical, which would be your CH3 dot reacting with a CH3 dot. And of course, that would give you a completely different alkane. That would give you ethane. So that would be CH3, which is, of course, ethane. Okay, so that's ethane right there. And the other possibility for a termination step is where you've got a methyl radical reacting with a chlorine radical, and thus forming another molecule of chloromethane. Okay, so this is another or a different kind of mechanism, because the bond breaking processes seen here are not heterolytic. You're not forming ions. What you're forming are radical species. Okay, so this is a radical substitution mechanism. Good. So having looked at all the different mechanisms we need to know at AS, let's have a quick look at a couple of exam questions to see what you will be facing in your A level. Okay, so here is a question. We're looking at compound A, and we're told that it reacts with hydrogen bromide to form a mixture of two different products. Give the structures of the two possible organic products. So might be a good idea to highlight what's required of us. Okay, so it says give the structures of the two possible organic products. That's one thing we need to do. We also need to outline the mechanism using the curly arrow model for the formation of one of the organic products from compound A. So we only need a mechanism for one of the organic products, and to finally explain which of the two organic products is more likely to be formed. Okay, so quite a bit to do here. So if we look at our compound here, so we can either form, so if we have CH3 and it is reacting with hydrogen bromide, worth highlighting that as well. So reacting with hydrogen bromide, so you could potentially form Br, CBr bond there, and so this would be one possible product. And you could, of course, also form this other product, which would be the alternative. Okay, so in this instance here, if we name them, so we've got here, so the parent name would be butane, and you've got a bromine and a methyl group. So this would be 2-bromo, 3-methyl butane, and in this instance we've got 2-bromo, 2-methyl butane. Okay, so these are the two possible products. So we've got the structure of the two possible products. Outline the mechanism using the curly arrow model for the formation of one of the organic products. Okay, so let's have a look at the mechanism for this product there. So if we start with our alkene, which is this alkene here, and we know it's reacting with HBr, and we know there's a dipole on our HBr, delta minus on the Br minus, and delta plus on the hydrogen, so delta minus on the bromine atom, I should say. The curly arrow starts from the middle of our double bond to the hydrogen, and then we break the HBr bond, like so. And then we've got our carbocation intermediate, which is, in this instance, going to be the tertiary carbocation. Okay, so going to form this and a Br minus ion, and then the charge is conserved. And then finally our product. Okay, so the question required us to outline the mechanism using the curly arrow model for the formation of one of the organic products. Okay, so double check our mechanism, starting from the source of electrons, going to the hydrogen with a delta plus, HBr bond broken, curly arrow starts from the middle of the bond to the bromine atom. We form our carbocation, the tertiary carbocation, and the bromide ion. And then, of course, in the next step, the bromide ion, the lone pair of the bromide ion, attacks the plus charge of our tertiary carbocation to give us our final product. Okay, and then finally, explain which of the two organic products is more likely to be formed. Okay, so the major product will be our 2-bromo, 2-methyl butane. So this is our major product. Why? Because tertiary carbocation formed from tertiary carbocation, if we write it properly. formed from tertiary carbocation, which is of course more stable. Why is it more stable? It has a greater positive inductive effect. Okay, so that covers all of the bases. So we talked about that being the major product because it's formed from a tertiary carbocation, which is more stable because it has a greater positive inductive effect. And you can show the positive inductive effect. We use red arrows to show that. There's the 3 alkyl groups contributing to that positive inductive effect. Whereas if we drew the carbocation intermediate for that, you'd only have positive inductive effect from that and that group there. Okay, so that is our a full and comprehensive answer to the question. 6 marks altogether. We scooped them all up. Okay, let's have a quick look at another question here. So this time round, we're looking at 6A part I, and we've got a halogenoalkane. It's a bromo cyclohexane, and it is reacting with sodium hydroxide, and we want to know what the intermediate product is. Okay, so that, of course, this reaction will be leading to the formation of the alcohol in a nucleophilic substitution mechanism. So there we have it. And if you wanted to show that mechanism, you'd have an OH minus ion attacking this carbon here, because that carbon has a delta plus, and bromine has a delta minus on it. And that bond is going to break the CBr bond to give us our product shown here. Okay, so that's our second mechanism, so nucleophilic substitution mechanism involving curly arrows. Okay, so before we sign off, I will just check that we've got questions, or perhaps no questions at all. Okay, so still no questions. What we will look at is, okay, so that brings us to the end of the session, but perhaps we want to look at this this step here, where you have the OH minus, so the OH group being lost as water. So this is an elimination step, the elimination of water. And the mechanism for this, you don't have to know on the OCR course, of course. So elimination of water, and that would require sort of acid, so phosphoric acid could be your reagent for this elimination here. So that. So H plus from phosphoric acid protonates the OH, and then the carbon oxygen then breaks, and you've got water leaving. And what you end up with is a double bond being formed here, so that you've got that alkene, cyclohexene, cycloalkene being formed. Okay, so thank you very much for joining me for this rapid tour of reaction mechanisms, organic reaction mechanisms from the AS year. Hopefully this has proved useful and sort of means that you're ready to take on the challenge of new mechanisms in your second year. As usual, I will ask that you go away and tackle some practice questions on the topic. And if you have any questions or come across any problems that you're not able to solve, to drop us a line at boostrevision.com, and I will be more than happy to reply to you and help you solve whatever problem it is. Thank you very much for joining me. It's been a pleasure as always. And our next year 13 session will be in a fortnight. I hope to see you then. Thank you very much.